Okay, let's now consider emission. Emission is the opposite process to absorption. So absorption was removing intensity from the beam. Emission is going to add intensity to the beam. So in the same way that looking at this cube, we could guess that absorption should be proportional to the length of the beam and to the density and to the incoming intensity, we can play the same game for emission. Again, you can imagine that if you have in this cube material that is adding light to the beam, that is adding intensity to the radiation, it's going to be proportional to the size of the cube, to the length of the cube, ds. It's going to be proportional to the density also, because if you have more dense, you have more emitting material. And in this case, it's not going to be proportional to the incoming intensity, because you can start from zero intensity and still have the material in here adding radiation. So then you're going to have a positive di coming out. So our guess is going to be that the outcoming intensity of emission is going to be proportional to the density and to the size of the cube, with the di being bigger than zero. So again, to make this an equality, we define a quantity that is going to be the proportionality. Call the quantity the emissivity and call it J. Again, the J is a function of the frequency because the material can emit a lot in one wavelength but not in another. So the intensity that is coming out of the beam is the original intensity added the integral of J rho ds. So we found both the absorption law and the emission law. You have intensity going through a cube. This cube has some properties: density, opacity, emissivity, and has a size ds. The intensity that is going to come out of it is going to be modified by di, given by a combination of the absorption minus kappa rho I ds plus the emission going through the cube, J rho ds. So we can write, based on this, differential equation if we divide both sides by ds. If we divide both sides by ds, we still have rho on both sides. Divide both sides by rho again. And actually divide them both by kappa rho. So then you have the differential of the optical depth. Substituting out the differential of optical depth, this equation becomes di d tau is equal to minus I plus j over kappa. We call j over kappa the source function. I'm going to reinstitute here the subscript frequency. This is called the source function. And then we find the final form of the differential equation of radiative transfer. The variation of the intensity with optical depth is going to be proportional to the negative of the intensity plus the source function. So this term here is absorption and this term is emission.